Andrew has also been a Foresight Fellow this year, and if you have shared somewhat of my Twitter subculture, it was very, very difficult to live on Twitter without hearing a few fantastic E11 announcements coming out recently. So I'm dying to hear all about it. Please take it away.
Thank you, Allison. All right. Hello, Foresight. I'm Andrew Payne. I'm co-founder and CEO at E11 Bio. And today I would love to tell you a little bit of a story around how we are moving brain mapping in very high detail towards very large brains, mouse, and eventually human. E11 Bio is a focused research organization, a nonprofit building tools to map the brain. So this year, connectomics, the science of mapping brain circuits synapse by synapse. This year, neuroscience has entered the connectomic era. We now have the first complete wiring diagram of a fly. And this wiring diagram is absolutely changing neuroscience. We are now able to attempt simulations of brain circuitry, which is constrained by the connectome. And we're going to learn a lot from those simulations. We're going to learn both what is possible and what is not possible. We might need other types of information like molecules or functional recording. But one thing that I want to focus on today is what goes beyond the fly connectome. What happens when we can map brain circuits at the scale of mammalian brains, of mice or humans? And it lets us ask questions that we can get at in no other way. For example, which brain disorders are so-called connectopathies? Literally defects in the wiring of the brain, and then how can we build brain-computer interfaces or drugs that restore that healthy function? It can let us ask, and I don't know why these are all ordered 111, but it can let us ask what blueprints are, for AI can we learn from studying the brain? What is it about mammalian brains that let us do, forward-thinking planning, curiosity, or even just having pro-social instincts? If we can figure out how that's implemented biologically, then we could learn from that and implement it in silico. And then finally, one thing that I'm really interested in is this question of, what empirical data is needed in order to simulate brains? And the first step is that we have to go and get the data. But there's a problem because scaling up from the mouse, from the fly to the mouse, is a 6,400 increase in volume and a 1,000-fold increase in the number of cells. And that's a challenge technically. And to give you a sense of just how much of a challenge that is, to attempt to scale up towards a single mouse brain today would cost tens of billions of dollars and take the better part of 2 decades. So it's cost intractable. What's surprising is that 97% of that cost is concentrated in that one block there on the right, proofreading, which is human annotators manually correcting the output of computer vision models that are used for interpreting brain images and reconstructing brain connectivity. So if you can address proofreading, you have an angle of attack on making the scalability problem more tractable. And so what we're doing at E11 Bio is that we're engineering the brain to proofread itself. We deliver something that we call prism tags to the mouse brain, and each neuron gets a different collection of molecules that allow it to function as a sort of ID code or barcode. And this helps us interpret which cells are which in brain images. And this is what it looks like. This is raw data from mouse hippocampus. And each of these colorful spots is a cell body. And if you just track this one body, we are reading out each of 18 different prism tags in order to construct a barcode for this cell. And we're doing this massively in parallel across the entire tissue slice. And once you have, say, an 18-bit barcode, you have over 240,000 possible combinations. And we have a roadmap to scale this to millions or even billions of combinations. And so when you take prism tags, and you combine it with advances in expansion microscopy, where we literally make the brain 20-fold bigger in order to see these thin structures like synapses and light microscopes, and we apply specialized computer vision models which can take advantage of these barcodes, then what we end up with is a technology platform that we believe can deliver connectomes at 100-fold lower cost than is possible today. And that's going to unlock mammalian connectomics. And so perhaps some of you have seen this video, but this is what it looks like when you have completely completed the process. This is a reconstruction of mouse hippocampal tissue. Each of these colorful objects is a piece of a neuron that we've mapped. And these glowing annotations are the synapses that connect cells to each other. And we've been able to do this at scale in one of the largest volumes for optical methods to date. And personally, I also just think it's beautiful. It reminds me of cherry blossoms. We've highlighted just a few cells in here for visual interest, but obviously this tissue is very densely packed. And as we get to the end of the video, what you'll see is that we have a faithful 3D reconstruction of the neurons in this volume with synaptic annotations. And we want to scale this further towards larger volumes and eventually entire mammalian brains. And so, just if you're going to take away a couple of things from this talk today, one, mammalian connectomics will transform neuroscience. We'll be able to ask questions that we can't get at in any other way. We need to eliminate the proofreading bottleneck to get there. And we think that our PRISM technology can deliver a 100-fold cost reduction. So with that, thank you very much. We, as Allison mentioned, did a release of our roadmap on Tuesday. So if you're interested in learning more, please check it out. We're also a nonprofit and super easy to collaborate with. So please drop us an email if you're interested in chatting more. Thank you.
Fantastic. Questions, comments? All right.
So for these iterative barcodes, I imagine that you need to get a lot of things to diffuse into the tissue repeatedly, and or is that not the case?
To read them out in microscopy, yes.
Right, and so I was wondering, like, how are you able to achieve efficient diffusion into the tissue, especially for deeper volumes as you scale up?
That's a great question. So this is a challenge in many methods. When you work with tissue sections, you can have reasonable diffusion times. And what we can do is we can use these barcode annotations to bridge across discontinuous slices, which allows you to process the brain massively in parallel across multiple microscopes, rather than trying to do it in one big block.
Thank you so much, Andrew.
Thank you, Allison.